Okay, thank you very much. Well, thanks for inviting and for introducing. Today I'm going to talk about Weyl algebras and generalized symmetries. It's my joint work with Roman Popovich and Dmitro Popovich. Well, if not the notion, but the concept of generalized symmetry can be traced back to the works of Amy Noether. And it is a kind of first step generalization of the concept of Lie symmetry. So in Lie symmetries, we consider vector fields whose components are smooth functions depending on dependent and independent variables of our system of differential equations. Those for generalized symmetries, we consider generalized vector fields. In other words, the components of the vector field of such form, they depend on so-called differential functions. So differential functions, these are functions on kind of finite order jet space. So they depend on finitely many jet variables. Vector field is called generalized symmetry if it satisfies the invariance condition. In other words, if you take prolongation, apply it to the system of differential equations and get zero. Well, this is the paper of Noether, where this concept appears in the first time. All right. Since we're dealing with jet variables, the computations here are much more complicated than those for Lie symmetries. Because we are, of course, dealing with infinite number of variables in particular. This is why there is not many objects, not many systems of differential equations for which these symmetries has been completely and exhaustively studied. To mention a couple of them, this Laplace equation, biharmonic equations, Klein-Gordon equation, well, of course, Burger's equation, as Professor Popovich has presented just a couple of talks ago. And at the same time, the study of the most basic model of mathematical physics, which is linear heat equation, was not completed until my work with Professor Popovich. Well, of course, some pieces of description of the algebra of generalized symmetry was distributed among the literature, but no closed form formulation of this proof, of course. So I'll start with linear 1 plus 1 dimensional heat equation. A very important step in study generalized symmetries for linear equation is the study of the Lie invariance algebra of the equation. The Lie invariance algebra of this equation is spanned by these vector fields. It's very well known. This algebra, it was computed by Sophus Lie. Here, this algebra contains infinite dimensional abelian ideal, which is spanned by these vector fields. Here, F runs through the solution set of this equation, and this ideal is associated with linear superposition of solutions. Algebra splits over this ideal, and the complementary subalgebra to the ideal is spanned by these vector fields, where I in purpose color them in red and blue, just to, well, this is for the reference paper with Professor Popovich, because we will see how the commutation relations behave. So here are the commutation relations between the basis vector fields of the essential algebra. Well, essential algebra, this is the algebra, well, that complements this idea. Okay, this algebra is non-solvable. Its Levy decomposition is given by this. So here R is spanned by Gx, Px, and Y is both radical and nil radical. It is isomorphic to the first Heisenberg algebra. And the Levy factor is isomorphic to SL2. And the action of the Levy factor on the radical is given by reducible representation of SL2R. This is the sum of weight 1 and weight 0 irreducible representations. Dimension of essential invariance algebra is 6. And this is, in fact, maximum dimension among the essential invariance algebras of linear 1 plus 1 dimensional evolution equations. And moreover, this equation is unique modular point equivalence in the class of linear 1 plus 1 dimensional evolution equations with non-solvable algebra G essential such that its dimension is 6. So it's a very specific equation in the class of linear 1 plus 1 dimensional evolution equations. It is the most symmetric one, and it is unique such most symmetric one, modulo the point equivalence. I present the algebra of generalized symmetries of this equation. This algebra is spanned by generalized vector. This algebra splits over the ideal that's again associated with linear superposition of solutions. And the complementary subalgebra is spanned by these vector fields. Here, G is a differential operator in total derivatives that is associated to the Galilean transformations. And dx is just a total derivative with respect to x. Lambda is a span of such vector fields. Okay, and well, this result was presented more or less in this form in this paper, in the CRC handbook, and this work of Krasilchik and Vinogradov school, and also using using these 3 papers, 1, 2, and 3 books by Oliver, by CRC handbook, and this book by Symmetries and Conservation Laws of Differential Equations, one could recover this algebra, but without the complete proof given. So this is why we revisited this in our paper. In fact, we showed a little bit more. We showed that this algebra lambda is isomorphic to the Lie algebra associated with the first Weyl algebra. This gives us a lot of insight about the structure of this algebra. In particular, this algebra has one-dimensional center. And modding out by the center, we get the simple Lie algebra. Lambda can be shown to be two-generated, and moreover, we could say even more. Well, it is two-generated, for example, by these sets of generators. As Lie algebra, of course, it is generated. Yeah, here A1R is the first Weyl algebra. In fact, Weyl algebras, well, it's quite unexpected although we have the radical is isomorphic to Heisenberg algebra, and it is well known that Weyl algebra is isomorphic to the quotient of the universal enveloping algebra of Heisenberg algebra by modding out the central element -1. Well, this is kind of why it appears here. Okay, I'll discuss a little bit of definitions related to Weyl algebra. Well, in the most generality, assume we are working over a field of characteristic 0. Then the first Weyl algebra is an associative algebra generated by 2 elements. We denote them by d and x that satisfies this relation, dx minus xd equals 1. This is the relation between derivative with respect to x and multiplying and operator of multiplying function by x. Weyl algebra is central, simple, Noetherian hereditary domain of Gelfand-Kirillov dimension 2. It is isomorphic to the algebra of differential operators with polynomial coefficients. Using, for example, Bergman's diamond lemma, one could show that a basis of this algebra is constituted by these monomials x to power k, d to power l, where k and l runs through the natural numbers with 0. Positive integers, yeah, non-negative integers. And the nth Weyl algebra is a tensor product of first Weyl algebras over the field K, tensor product of n copies of the first Weyl algebra. And in fact, nth Weyl algebra is isomorphic to this quotient of nth Heisenberg algebra, modding out this the two-sided ideal generated by C minus 1. Well, it's a lot of known about the structure of this associative algebra. The thorough study was initiated by Dixmier in his seminal paper, and well, a lot of open problems are known for Weyl algebra, which also related to the so-called Jacobian conjecture, but I'm not going to talk about it today. Okay, next equation that I actually started my master thesis with. Well, I began my collaboration with Professor Popovich considering this equation. So this is a so-called remarkable Fokker-Planck equation. We proved that this equation is well, first of all, it's clear this equation belongs to this class of two-dimensional ultraparabolic degenerate Fokker-Planck equations. Well, the preliminary group classification of this class was carried out by Davidovich, and actually we know the classification, the group classification for this class, and our approach was based on the paper by Gonzalez Lopez, Camran, and Olver. Well, this equation belongs to this class, and it corresponds to setting up the coefficients b to be x, a to 1, and a1, a0, c equals 0. Dimension of essentially invariance algebra is 8 of this equation, and it is up to the point equivalence a unique equation from this class that has this property. Well, Kolmogorov constructed the fundamental solution of this equation. Well, some references for preliminary study of this equation, and reference to my paper with Professor Popovich and Dr. Bila on the extended symmetry analysis of this equation. The Lie invariance algebra of this equation is the span of the following vector fields. Here again we have ideal associated with linear superposition of solutions, and the algebra splits over this ideal, and the complementary subalgebra is called essential subalgebra, is spanned by these vector fields Pt, dk, p3, p2, p1, p0, I. I present well, here you could find the commutator relations. You could see the commutator relations between the basis vector fields of this algebra. And using these commutator relations, we could describe the structure of the algebra. Well, the algebra is non-solvable. Its Levy decomposition is given by this semi-direct sum. So R is a radical and nil radical. R is isomorphic to the second Heisenberg algebra, and Levy factor is isomorphic to SL to R. And the Levy factor F acts on radical via the reducible representation of SL to R, direct sum of highest weight 3 and highest weight 0 representation. Well, this is reminiscent of that for heat equation. For heat equation, we had here 1, and the representation was ρ1 plus ρ0. Well, to describe we computed the algebra of generalized symmetries of this equation. Well, to describe the algebra of generalized symmetries, we introduced the notion of Lie symmetry operator. Lie symmetry operator of a homogeneous system of linear system of differential equations is a first-order linear differential operator in total derivatives, such that the tuple of functions Qu is the characteristic of an essential Lie symmetry of L. So if we apply this operator in total derivatives to U, we obtain a characteristic of an essential Lie symmetry. For example, in the case of this equation, the Lie symmetry operators corresponding to these vector fields, well, the signs are chosen for convenience, well, as these operators. P3, P2, P1, PT, D, and K. And in fact, one could show that PT, D, and K are lie in the associative algebra generated by the operators P3, P2, P1, and P0. Well, yeah. Well, when considered when considered on the manifold of the equation, so when the derivative with respect to t is changed with respect to this equation. Well, the associative operator algebra that is generated by these operators P3, P2, P1, P0, it has this presentation. And it is isomorphic to the second Weyl algebra. Well, theorem that the algebra of generalized symmetries of this equation is a semi-direct sum of the subalgebra of linear generalized symmetries. Yes, the subalgebra is called subalgebra of linear generalized symmetries, and the ideal associated with linear superposition of solutions. And in fact, this algebra, lambda, is isomorphic to the Lie algebra associated with the second Weyl algebra, which is again very reminiscent of the situation with the linear 1 plus 1 dimensional heat equation. So we could put these two equations, in fact, into a broader context. Well, we did some computations for, so consider this equation. Ut plus sum I running from 1 to n minus 1, xi, u derivative with respect to xi plus 1, and this equals the second derivative ux1, x1. Well, this is this belongs to the class of ultra parabolic equations in 1 plus n variables, such that the matrix of coefficients of this left-hand side is degenerate. And in fact, if n equals 1 and n equals 2, these equations coincide respectively with linear 1 plus 1 dimensional heat equation and remarkable Fokker-Planck equation. Well, basing on our computational experiments for a small number of n, we could make the following list of conjectures, which is very interesting for to investigate. So dimension of essentially invariance algebra of equation Fn is 2n plus 4. And this essential algebra is isomorphic to the direct sum of SL to R and nth Heisenberg algebra. And the action of SL to R is given by this by this reducible representation of SL to R. And moreover, we could state that the dimension of essentially invariance algebra is unique in the class of the ultra parabolic equations in 1 plus n variables that I mentioned in worst. I didn't want to write it because it would take a lot of space. Okay, essential point symmetry group of this equation is isomorphic to this Lie group, which is direct product of SL to R and nth Heisenberg algebra. This is the representation of SL to R on vector space, but you could define the action of SL to R on H and R, which is kind of respective to this representation of SL to R, n times the 2. There is a unique discrete symmetry of this equation. Well, modulo combining it with symmetries from the connected component of this group. The algebra, the generalized symmetry algebra is such semi-direct sum, where lambda n is generated by acting with Lie symmetry operators associated with the canonical basis of the complement to the center u du in the nilradical Rn of G essential n. Nil radical is isomorphic to this Heisenberg algebra. And sigma minus infinity is the ideal associated with linear superposition of solutions of Fn. And also, the algebra of generalized symmetries is isomorphic to the Lie algebra associated with nth Weyl algebra. In particular, this algebra is Z-graded. Professor Popovich mentioned this the construction of the gradient on the first Weyl algebra, but that construction could be generalized to any Weyl algebra. And moreover, this algebra lambda n is too generated as a Lie algebra. Well, this is it. This is what I wanted to tell for today. Thank you very much for your attention. If there are any questions, I'll be happy to answer them.
Thank you for your talk. Yes, we are waiting for questions if there are.